on this computer. All right, all set. Hey, hello everyone, and welcome to today's code walkthrough about drand's storage and sync functionality. So I have only one slide today, and then we will jump into the code directly. So here is what we'll be talking about today. So first, the drand config directory. So what kind of files drand needs, what kind of files it creates, how the structure looks like, and so on. Then we'll talk about the type of stores, which are different ways we are storing data in drand, and actually there is some kind of storage wrapping happening, and we will talk about these different stores as well. And finally, we'll be talking about the sync process, the difference between syncing and catching up, the notion of following a node. Let's say you're a new node and you want to follow another node because you haven't joined the network yet. The notion of resyncing a node, because we have a functionality that allows you to resync. Overall, when does syncing happens, and the code of the sync manager, and yeah, what it's doing basically. So without further ado, we can jump into the code base. So I am showing you the develop branch. I'm not sure we can't see it here, can we? Here, the develop branch, which is our current development branch that is going to become the next major version of drand, which we'll be releasing probably later this month, maybe next month. So it's the up-to-date code, basically. And so when we talk about drand, we have seen already a couple times the different kind of folders and files we have in the repo, but everything really starts in the drand binary here, which is the command drand main.go file. And you can see we're running an app called drand CLI. And in the drand CLI, we are defining all the different kind of commands you can run, and all the different kind of flags you can use with the drand daemon. And so you can see here, we've got the, for example, the verbose flag that allows you to tell your daemon that you want it to log all detail of what's happening. You have the folder flags that allows you to tell it where it should be finding its config folder. And then you have all the other flags that are added to each of the commands, and we will see that here. Well, we don't really see it, but it's basically if we go down, if we go up actually here, if we go up to the definition of all the commands, that's what we have here, the app commands, for example, which include the DKG commands, which are in another file here with the different DKG commands that Patrick presented a couple code walkthrough ago. And then we can see the most important one probably is the start command to start the drand daemon. It contains quite a few flags you can specify, and the flags we're very interested in today are the folder flag, the storage type flag, somewhat maybe these two extra flags that are related to how the storage works. But so the first thing I was mentioning is the folder flag, which is basically a flag you can provide to the command to tell it where drand should be keeping all of its data. And that's supposed to be an absolute path. So that's the trick. Never use relative path for that one. And so, for example, if I go to my tmux here, we can see I have a couple terminals open, and here I can make drand that should build the daemon, and now I have a drand binary that is running the latest version of the code. We can check the commit if we want. We can see that is the commit we're supposed to be running, and that corresponds to the commit here in short form that we are using. So that's the latest version of the code base. And if I run drand start like that, it will complain to say it doesn't work because it doesn't like something. And the some things it doesn't like is the fact I haven't specified here a folder flag, because by default, if you don't specify the folder flag, drand will use the drand folder in your machine. So depending on your home directory location and user and different things, it can be tricky. So if you run drand as root, for example, but also as a user and a server, sometimes if you just run the commands without specifying the folder flag, you might have multiple users with a .drand folder in their home directory, and that can cause a lot of issues. So here you can see I have a .drand folder, it seems, in my home directory, but I don't want to use that one. So instead, I am going to tell drand to use a folder I've prepared one, drand s.5. That's the folder I've prepared with 3 different nodes in it, 3 different folders. And so what I've done to prepare these folders is basically generate a keeper for 3 nodes, B1, B2, and B3, with different addresses on localhost. And then I've also done a DKG, just like Patrick showed in the previous code walkthrough. So we have 3 nodes ready to start in theory. So if I do just that, right, it won't start, because I need to tell it it doesn't need to use TLS to run. I named it no TLS because I'm not using TLS locally here. Also, I need to provide it with a private listen address so that it knows what port to listen on gRPC incoming connections from other nodes. So here I'm running it on localhost on port 701 for the B1 node. And then, oh, I didn't specify private listen. There we go. So drand start, specifying the folder, and now it will fail for some reasons. Oh, well, I told you not to use a relative path, and I did. And that is unexpected, so I guess I have some issue with my let me try with the other binary I used to create the okay. So I guess I got some issue with my repo locally. Anyway, so here we have a node running. It's alone. It's not very happy, but it's running. So we can see it started using drand 157, which is the version I used to create these files. So I guess we need to double check compatibility between the develop branch and the master branch anyway. And so once the daemon has started, what it will do, I can actually terminate it. What it will do, you can see, is register a new beacon handler, and we've presented that in one of the very first code walkthrough, and then it's starting to try to sync with other nodes because it's an existing node, and so it's detecting it's late. It should have more recent beacons, and it's not finding them in its database, and the database is located in that folder here. So if we go and see the structure of that folder, we can see we have the default beacon ID, which contains the drand DB file, the groups folder containing two files, the dist key private and the drand group.toml. And then we have the key folder that contains the private and the public key for these nodes. And so if we look at all the other nodes I've prepared for today, they all have the same structure. So you can see they have a multi-beacon folder. So that is because previously drand was meant to run with a single beacon ID, which was the default one, and all of these three folders here were stored directly in the config file of drand. But with the version 1.5 of drand, we've released the notion of being able to run multiple beacons at once on the same node. And so here we are running the default beacon, but we could be running a fastnet, a quicknet, we could be running multiple beacons at once on the same node. And so they would all have their own folder in the multi-beacon folder, in the drand configuration folder. One file here of interest is the drand DB file. So I can drand DB file. The drand DB file is a bold DB file, so I can use the bold browser CLI tool to basically open it. And see what it looks like inside, right? And so inside we can see we have 4 beacons, and we can see the beacon has this value here, and it's a weird, binary value. So that is not super useful for us. We used to store the beacons in hexadecimal, so you could read them easily using bold browser or whatsoever, but that was really a waste of space because in the database you can just store binary directly and you don't waste any space. And so that's one of the things we've done earlier this year. We've released 3 new drand storage backends basically, and so I'm going to introduce them now. So if we go back to our code base here with our different flags, and we've seen how to run the start command using the folder flag to specify the folder, the config folder location. Now we can look up for the storage type flag here. And so you can see that's another flag named DB, and its usage says which database I'm trying to use. Supported values are bold, Postgres, or memdb. And these are the 3 different type of storage backends that we support. If we try to -H here, we can see that is the flag we're talking about now, and its default value is bold. That's also something you can see here, that the default value is bold. So obviously, as you might have guessed, if you use the Postgres value, then it means you want to run a Postgres SQL, you want to connect to a Postgres SQL database, and then you need to provide some extra details. And that's why you have another flag here, the PGDSN flag, to provide the PostgreSQL DSN configuration details. So typically that would look like this: Postgres 2.// some address, some user, some database name and user and IP and port, and then some extra details, maybe if you have a specific connect timeout or whatsoever. So I'm not going to demo it, but that should allow you to run your own PostgreSQL database instead of using your localhost storage to store drand nodes. So if you want to decouple the storage of the beacons and running the daemon, you can do that using PostgreSQL, which can be fairly interesting depending on your setup. The other interesting thing we have is the memdb option. So memdb stands for in-memory database, and it basically means drand is not going to store any values locally on your machine. It's going to connect to the other nodes in its group file, fetch the latest beacon from them, and it will bootstrap from that latest beacon after having verified the group using the group public key, the signature of the beacon, because then it knows it's a legit beacon from the group, and it can bootstrap from there and operate as if it had a local database. It also means if you're querying beacon number 2 on a node which is running memdb, you might not be able to get it because by default, the memdb buffer size is 2000 beacons. So it must be at least 10. We use 2000 as a default. It's not using a lot of memory, and it's also much faster than the Bolt or Postgres backends. So you can use a larger value if you want, but let me do maybe a quick demo. So if we come back here to our nodes, right, we can go here. We can run the first node. We can run the second node. Doesn't like something. Oh, I didn't specify in second. I'm using /drand. Okay, we're running the second node. And now I can start my third node using the memdb, for example. I use the memdb. I didn't specify insecure. Okay, and so now if we, as we can see, the nodes are catching up, and that's using the sync. So that's using the catch-up, sorry. So when you have a problem and the network stops, the nodes can know, given the genesis time and the period, at what beacon round they should be at, right? And so they can detect there is a time discrepancy, which we can see here in the logs. Whenever we store a beacon, we store also the time discrepancy with the expected time for that beacon to be stored. And so if they detect a discrepancy that is bigger than the period, it means they're late and they need to catch up. And so the node will talk to each other and start producing nodes, well, partial, much faster than they usually do. We've seen in a previous code walkthrough the way we have a run loop that is basically producing partial signatures every 30 seconds or every 10 seconds, depending on the period of your beacon chain. So if your node is late, it will basically start sending partials much faster. You can configure the catch-up time during the sharing process. If we look at the run share command, you can see here there is we can see here there is where is it? Catch-up period flag in the share command that allows you to say do not catch up too fast. That can be useful depending on what you do with the randomness, because then if you're expecting some round or some beacons to be produced before other beacons are produced, because otherwise it will be a problem for the security of your system, you might want to have a catch-up period that is bigger than 0. Currently on mainnet, the catch-up period for the default network is 15 seconds. So we produce one round every 30 seconds by default. If there is a problem, the network goes down, the network will catch up with its expecting round at twice the speed, basically, because it's going to produce a beacon every 15 seconds instead of every 30 seconds. We have just launched the QuickNet network on mainnet, and this is using a 3-second period. And so we've tweaked the catch-up period to catch up at a 2-second frame. So it's going to produce a round every 2 seconds until it has caught up. That means if you're using one round every 30 seconds, you have a catch-up period of actually 20 seconds instead of 15. So it's not exactly the same as using the default mainnet. But anyway, we never had downtime since 2020. So the mainnet nodes are not using the catch-up code too much. The other thing that is happening once the network has caught up is that the nodes that are lagging behind, so for example, if I stop this node here, the other 2 nodes will keep producing new beacons. So we can see here, it's going to produce a new, so here we can see error sending partial, because it couldn't deliver the partial to one of the nodes, but it still got a partial from the other node, and so it was still able to produce a new beacon, because here I have a threshold of 2 out of 3, and so it worked. Now, what happens when I restart my crashed node here? So what happens is the node will detect it's late, and it will start syncing with the rest of the network. And so that's what is happening here. It's synced with the network. And that is not obvious here. Oh yeah, here we got a gRPC client chain sync context canceled error because it canceled the sync process with one of the nodes. And here we can see it tried to store a duplicate beacon for a round, but the previous sync was different. And then it still tries to catching up. So this node is currently not really caught up with the network. It's still probably syncing, and it had some issue catching up. I don't know what's happening. But if we want to see more details, actually, it's very interesting to use the verbose mode, because the verbose mode is going to tell you everything the sync manager is telling you. So here we can see suddenly way more lags because I stopped it for a little while. So when it started again, it detected it was late probably, and then it started syncing. So here we can see sync manager says starting new sync, started sync up to around 500. It's trying to sync with all of these nodes here. So by default, it will sync with all the nodes in the group file. So and here we can see start skipping sync with our own node, obviously, because in the group file, we do have our own node. So we don't want to sync with our node. We want to sync with other nodes. And then, basically sync happens. One thing that can happen, though, is when you try to do a sync with the network and you're also almost caught up or completely caught up, it might be the case your node is both receiving a beacon through the sync manager sent by another node, and it's also trying to store a beacon it aggregated by aggregating all partials together. And that's exactly what happened here. We had a race during aggregation between the sync manager and the main partial loop. So that is handled by the node. It's not going to cause an issue. And once the node has caught up, we can see it start sending partials again. So now I've stopped that node again for a little while. So now if I start it again, we should see it's going to store a few beacons, start sync, and then it fetched 3 beacons, and then it started sending partials again. So that is not very interesting because it's syncing very quickly. So one thing we can do to make it more interesting, this is node 1. So we can delete the database of node 1. Okay. So now I'm going to start my node. It's going to fail to see any beacons on disk, and it's going to start aggregating, well, not aggregating, it's going to start syncing with the rest of the network as quickly as it can, and it can do so very quickly. As we can see, we already caught up, and now the database is up to date again. So that's for a node that is already in the group file, already running, already allowed by the allow list. So other nodes allow the node to connect to them, and it just works like that. Another use case we have for the sync manager. So let's go and see what the sync manager does in the code base. So here, we can go in the sync manager code. It's in the internal folder, chain beacon, and it's here in the beacon folder, sync manager. So the sync manager is basically receiving sync requests and sending sync requests to itself. And then it's a big, just like the handler for the regular, just like for the partials, it's a big loop. And whenever it needs to process a new request, it's going to take the request, check if we really need to sync, because maybe we stored the latest run already, and so we don't need, so it would cancel in that case. We keep track of the time since we received a new round. And then if that time is, smaller than the clock, then we will start a new sync. And the new sync is happening in its own Go routine. Here we do Go as sync for a given request. We can go and see the sync code here. The sync code is going to take all the requests nodes. So a request is sent from our daemon to our daemon locally. It's not going over the network, so that might seem weird, but we'll see in a minute why this is useful. So it's going to take all the request nodes. So by default, the sync manager is going to request all the nodes in the group file. It's doing a random permutation of them so that the first node is not always the one getting hit, by all the other nodes trying to sync. If it's our own node, we skip it, and otherwise we try to sync with that node. And trying to sync is handled here in the try node, and that's a lot of code basically, because there are a lot of edge cases that can happen depending on the request we received and everything, and because also that code is a bit overloaded because it's handling the syncing, the resync, and also the following logic, which we'll see in a minute. So that is doing a lot of things basically. We've been discussing refactoring it. We'll see, maybe we'll get to it at some point in the next few months. So the interesting thing here, I guess, is basically that it's going to create, it's going to receive beacons. And how is it going to receive these beacons? It's going to receive the beacons through the sync chain command. The sync chain command is run through a client. So we have a local client here, protocol client running in the sync manager. And that client is going to run the sync chain logic that talks to the gRPC interfaces using gRPC and everything. So if we look at the drand, the sync request here, let's look it up, we can see the drand beacon is implementing the sync chain function that takes a sync request in from the gRPC servers, or through gRPC rather. It's going to check which beacon ID it's meant for, and then it's going to grab that daemon process, the BP variable here, and it's going to forward that request to the sync chain function of the beacon process. The beacon process is receiving these sync request, doing some sanity checks, and then it's going to fulfill it using the sync chain function, which is a fairly simple function. You can see it's not attached to any struct, so it's a standalone function. It's taking a store, a callback store specifically, is getting a sync request and a sync stream, and then it's going to basically load for that beacon ID. It's going to load so from the store, it's going to grab the latest round and everything. And so it's going, if you go down a bit here we are, cursor. So it's going for that store. It's going to go through all the beacons, and it was going to send the beacons, and the send function here is defined here. It's going to send the beacons on the stream here. So send packet. So what it does is it's taking a store, which is a callback store. We'll see why in a minute. And it's getting a request and a stream, and it's going to send on the stream all the beacons requested by the requests that are stored in the store it's provided with. So I just talked about the callback store. And one thing I mentioned in my initial slide is we will see the different type of stores. So in drand, in the internal chain beacon store.go folder, we have quite a few different types of stores interfaces that are defined. So here we can see the callback store, which takes a chain store. So we have a chain store default kind of interface, and that's the interesting one. The store interface here is defining all the important functionalities for storing and getting beacons from a database that drand is using. So we can see the get function, the last function, the put function, the len function, the close function, the delete function, so we can delete beacons in a database, and the save to function that allows you to basically write, it's a backup functionality. So our different type of stores are all implementing these chain store interface, but they have extra functionalities. So here the callback store allows you to add a callback, okay, which has a given ID, and that is providing a callback function. So here the callback function is a function of a beacon and a closed bool. And what it does is basically every time it stores a new beacon, it's going to run that callback function. So in the case of the sync manager of the syncing, we register a callback that says every time you store a new beacon, if you haven't yet fulfilled the request and you're at that point, send that new beacon to the stream that requested it. You can also remove the callback, obviously. The other bit of logics we have here in the beacon store.go folder are the append store, which is a chain store as well, but it also has the notion of latest beacon. So the last beacon is the last beacon it stores, and it refuses to store a new beacon if that new beacon does not follow directly that previous last beacon it stored. So that is implemented here by somewhat overloading. I know we don't really like to talk about Go code as if it were, C or C++, but you can actually somewhat overload functions when you implement them through interfaces and structs like that. So here, when you create a new append store, it takes a store as input. So you need to provide it with another store that's going to implement all the other functionalities you need to satisfy here for the chain.store interface. And then for the put functionality, we overload it here using this function put that is going to check the append store last round against the beacon round we're trying to put in the store. And if it's equal or if it's not, exactly the last round plus one, if the beacon round is not last round plus 1, then we complain invalid round inserted, because we tried to store something that was not directly following the previous round we've stored, the previous beacon we stored. We have a few other stores, quite a few of them actually, if we go down here. So we can see a lot of logic around the callback store, because that's what I was telling you. Basically, every time you put a new beacon in the store, what you are going to do is for each callback function you have, you're going to create a new job with that callback, and you're going to send it the callback and the beacon. So even if it's a function that takes a long time to execute, you're going to execute it in the background using the workers you're defining here. So you have some workers running for all your callbacks, and so it's quite a bit of logic, but it's not too bad. The other thing you can see here is the discrepancy store. So that store is there just to log timing information about the round. So this is a funny one, because its only goal is whenever there is a put functionality, the put function is called, what it's going to do is it's going to put it in its underlying store, because as you can see here, a new discrepancy store is instantiated by providing it with a store, a logger, a group file, and a clock. And so it's going to store it in its underlying store, which might be a callback store or an append-only store, or it might just be the default bolt DB store. It really depends on what you do. And then here, it's going to run some computations and display a nice new beacon stored time discrepancy storage time millisecond log line, which you've seen quite a lot here. If I go back here, every time we store a new beacon, here we can see this new beacon stored. That is this line. So this is displayed in the logs because by default, the store we're running in drand is a discrepancy store. And if we go to the place where we instantiate all of these, actually, we can see here we have the new chain store. I talked about it a while back, I think in the first or second code walkthrough, but it doesn't hurt to recall it. So we have the new chain store that is being called in the new handler function, which is being called in the new beacon function of the beacon process. Okay, so the beacon process has a handler that is handling partials and also storing beacons. And that handler, when it's getting created, is going to instantiate a new chain store, and it's going to provide it with all of this data here. And the new chain store it's instantiating is a discrepancy store, it's a scheme store, it's an append-only store, a new append store, it's a callback store, and that's it. So what that means is every time you store something in the chain store of your drand process handler, you're going to log the time at which you've stored it. You're going to check the crypto, the underlying crypto that is specified in the group file. So if the signature is valid and stuff like that, you're going to check it's directly following the previous beacon you've stored. So you cannot store beacons that are not, following each other's. And you're going to run all the callbacks you're supposed to run according to your callback store. So that's quite a lot of logic, but it's all mingled into a single CBS callback store, which is getting passed to the sync manager, and then also passed to the callback store of the chain store you're creating here in the new chain store function. So one thing you might be asking is, where did the database come from here? None of it here is referring to any database. So what happens when we do a put? Well, actually the discrepancy store takes a store as argument here, and that store is specified here as a chain store interface. in the new chain store function. So you might be asking yourself, what's going on? We're creating a new chain store with the function new chain store, but we're supposed to provide it with the store chain store argument. Then it's going to return a chain store object, well, pointer to a chain store. What? Well, these are not the same chain stores actually. So here we have the chain store struct with all the data we need to basically run the process. But here, the store we're passing is just an object satisfying the chain.store interface, which is just this function I've told you about earlier. So these function I've told you earlier are actually implemented here. You can see here we are passing the S value, which is coming in the new handler from the arguments as well. And so if we go to the beacon process code, creating a new beacon, we can see we are passing it a store here, and that store is defined here by running the beacon process create database store function. That is where all the store, I don't know, Pinata is ending. So the create database store is the place where you create a chain store, where you create an object satisfying the chain store interface. And that object can be either, as I told you, the BoltDB store, the in-memory DB store, or the PostgreSQL store. That's really where it all happens. There is one trick, since I told you earlier, we changed the format of our BoltDB database. We actually do have two different ways of doing BoltDB. So you can see here we're calling the new BoltDB store, but we also have an old BoltDB store, which is basically storing beacons in hexadecimal instead of binary. But the new BoltDB store is the one we're using now. And that is where the database is actually being opened. You can see here, and when everything is happening, that is, allowing beacons to get stored on disk. So that was a lot of things, I guess, but I was coming from the sync manager, just syncing beacons and storing beacons. And so the other thing the sync process here can do, so you have the syncing and you have the catch up we've mentioned. So catching up is when the whole network is lagging behind and needs to catch up to the current time. And syncing is when a single node needs to sync with the rest of the network. Now you have this notion of following a node. And that is very interesting if you're running a node as an operator, because when you create your node, right? So you can see here, we got all of these existing nodes that are at round 581. So now if I'm here and I do generate keeper for my, oh, I don't remember. That, okay. I don't remember which scheme I used. So, okay, I used the Pedersen BLS Unchained scheme. So now if I do generate keeper, and I create a new B4, okay, node using the scheme in secure mode, so user TLS, and it's going to be running on the address localhost 704. I think I got it all here. Yeah. So now what has happened is I've created a new folder for my new node I want to create, right? So we can check it out here. You get this new folder. It's got only a drand ID and Yeah, it's got only a private and a public key in the key folder. It got no group file. It's also got no database, right? So my node here, I can start it if I want. I can start my node in. Oh, I don't need the scheme command here. Oh yeah, I need to specify another control port. Okay, so my node has started. It's read it's been reading its local config directory at TLS and at test 157 no TLS before, and here it says folder here, and it's found nothing, so it says ready to run as a fresh install. But the network has been running for a while, so it's much ahead of that node. So if we were to do a resharing now, that node would be lagging behind and consuming a lot of resources to catch up, and it's a bit annoying. So there is basically two options to catch up with the network easily. The first option is to copy simply the database of another node, okay? So the problem if I do that with the node running, I might be getting a database that is in a dirty state. And so I don't really want to do that. So I would need to stop my node, do a copy of the database, and then I can start again. My other node will catch up, and that node will have some beacons in its database locally. So I could do that, right? I could store it in the B4 folder at the location it's supposed to go, right? But, it's not great because every time a new beacon is stored on the network, I would need to copy a new or I would need to do that again or whatsoever. So it's not so great. So the other thing we can do is when we already have a drand node running like that, we can actually tell it to follow another node, and that's where the sync. That's where the sync. Oh, let me go full screen. The sync follow is interesting. So it indicates whether we want to follow another daemon. If not, we perform a check of our local DB. It requires to specify the chain hash. Okay. So here we can tell it using the follow function. On the sync nodes, we need to tell it against which node to sync, basically, because it doesn't have a group file, so it doesn't know anything about the existing network. We can tell it, hey, just follow that node, and we need to tell it on the right control port, so that would be 904. What happens if I do that now? It's going to fail because I didn't provide a chain hash. And so I need to get the chain hash from the other nodes. I can do that by just looking it up, I guess, in the I can do that by looking it up in the group file. In practice, I would actually look it up on the /chains endpoint of an HTTP relay, right? But I don't have a HTTP relay running here. So, oh, it doesn't work like that actually. What I want to do is get the chain hash. So I need to get, yeah, I can do it with the get command actually, yeah. Info. So chain info, okay. Here I get the group hash. No, I don't want the group hash. I want the chain hash. That's the one. All right, so now I can sync follow, and I need to provide it with the chain hash value. it. Oh, and now it complains because I haven't told it to run in secure mode, I guess. I did generate my keeper using insecure. I am running my node with insecure.
TLS disable maybe?
It's a synonym. Okay. I have no idea what happened. So here we can see my node is following that other node. And so as long as I'm keeping that command line open here, it will sync with the so here I've told it to sync with the node 701. I could sync with more nodes. I could put more nodes in here. The sync node command actually takes comma separated list of nodes. And yeah, you can see it's updating, and we're currently at the current target. We're at 100%. We're completely synced, and we're following the chain as it goes. So as an operator, that's an easy way of following another node. Also, if somebody is running HTTP relay, for example, they might not want to connect their relay to their production node, because if something goes wrong, the node could go down. So instead, they can, if their HTTP relay connect to a node that is actually following their main node. So that's a useful thing to do too. And so here we can see, I haven't run that one with verbose. Let me do it. Here we can see in the node following that it's running the sync manager code, and it's following, basically it's launching follow now, it said, and it's added a callback for that node it's following. Yeah, that is just running as expected. If I cancel, and that is something that is not always the case with drand, but if I cancel the command that the client is running here, if I cancel it, it will stop on the daemon as well. So that is unlike the share command, where if you cancel the share command, it completely stops. Well, it doesn't stop the DKG, it keeps running on the daemon. So here, for the syncing and following, when you stop it, it just stops. And we can see tests folder. We now have a D or multi-beacon DB folder containing the drand DB, and that one is not it's not empty anymore. So it's really stored on the daemon that is running the follow command. And yeah, I've been talking a lot, I guess, so we still have a minute or two for questions if there are any. But yeah, that's it, I guess, for my code walkthrough for today. I can also stop the recording, I guess. Let me stop it.